Hello there. Today I would like to talk to you about finite state machines, what they are and what they're used for. So, after I finish writing this, let's just do a small diagram here. So a finite state machine is a machine that contains a set of states. The machine can only have one active state at a time. So let's say we've got a state here of on, we've got a state here of maybe on, which doesn't really make sense, but would be valid, and then we've got a state of off. Only one of these can be valid. This is a very useless practical state, but that's fine. So only one of these can be on. How do they work? Well, to change from one state to another, so from on to off, we have to provide some kind of input. So in this case, we can just say x is 1, and then it will turn off. And if we want it to go from off to on, we could say x is 1 as well. So if x remains on, it'll keep switching between on and off. However, as x is an external input, so to speak, as soon as you change state, it'll be reset to 0. Well, hopefully it will be reset to 0 in this circumstance, so that next time you turn it on, it'll actually switch properly. What are these used for? Well, in game development, which is what we're doing, they're used for things like a character controller. You could have a character which has a walk state, jump state, an idle state. These three, let's just go with that for now. Then it has a way to change from idle to walk, from walk to jump, from jump to idle, from jump to walk usually, walk back to idle, and then from idle to jump. So it will usually look something like this. In fact, the Unity animation controller might be familiar to you if you've dabbled in Unity, and this is, I believe it's just a state machine. Yes, actually they refer to it here as a state machine. So if we have a look at this, yeah, here's the diagram I was pretty much just drawing. It's a little bit more complicated, I guess. It's just got some extra states. So only one of these can ever be active at a time. You can't be standing, jumping, and also running at the same time. This is running, I guess. Interesting. So they're used for character animations. They're also used for some other things like, well, they could be used for some other things, like let's say you have a game and you have a main menu. My handwriting has horrible. Main menu. And you have a town. You have a battle. And these are kind of like the screens that you're in, what current state, I guess you could say, you are. So you can actually use a finite state machine to check, okay, what is the player seeing right now? If they're on the main menu and they click new game, where do they go? They probably go to the town, for example, in my game, after some cutscene or whatever, right? And then if they're in town and then they choose to fight something, or maybe there's another state here called explore. Right, so they're exploring right now, so they go from town, they're exploring, then they go to battle, then maybe from battle they go back to exploring, and then you get the point. Exploring, they go back to town, they quit the game, they go back to the main menu, exit, whatever. So you can see these things are useful across a variety of different circumstances, but only useful when you have one thing active at a time. So, okay, let's do a simple example here. We'll have an off state, on state again. Okay, we're gonna Okay, this can be this can be this, x equals 1, x equals 1. So if we're currently on and x changes to 1 or is 1, then we go to off. And if we're currently off and x is 1, we go to on. The way to visualize this in a way that kind of makes sense for figuring out what the next state should be is by using something called a truth table. We're going to do that now pretty quickly. So we've got x, here's the input, we've got state, and then we've got the next state. This should be pretty simple. So we can have state is on and x is 0, state is off and x is 0. Or we can have x is 1 and 1, and then state is on, state is off. Alright, so if the state, if x is 0, we know that we're not going to change, so we can just copy state from here, because that does nothing. If x is 1, we know we can change, so we just reverse these in this circumstance. Alright, that's pretty simple. And you can use this information to kind of batch, I guess, bake behavior. So you can make a table. Actually, I'll go into that a bit later. First, let's see if we add a on, off, and I'm going to go with maybe on again. But that doesn't make sense. Maybe on. And now we'll say that we're on and y is 1 and x is 0. Then we go to this maybe on. And if we're maybe on and y is 1 and it doesn't matter what x is, then we go to off. So now our table becomes a bit more complicated. So what have we got? We've got x, y, state. So these are called inputs. They're inputs into the machine to make it determine which state it should be at. And next. Alright, so I've drawn out the appropriate combinations of x, y, and state. As you can see, it gets large very quickly. We've only added a couple of different things here. And now to fill in the next, you can just refer to this diagram over here. It's pretty simple. So 0, 0 on, we don't go anywhere. And 0, 0 off, same deal. And on maybe, same deal, because we need the y to be 1. Okay, now 0 on the x, on the on and off, we're not going to go anywhere. Actually, on the on we might. 0 on the x, 1 on the y, on the on, we're going to go to them. So I'm going to put a little star in front of here if the state actually changes. Alright, this example actually has a lot more state changing than some other ones that I've run through. That's because of the permissive nature of these. So if we actually set this to y equals 0, y equals 0 on these two, so it's only when x 1 and the y is 0, then suddenly, where are we? Y equals 1, or on, I can go to maybe. Yeah, but sorry, x is 1 and y is 1. So these will all be wiped out here. You can kind of think of these inputs as permissions for these to change to a certain state. Alright, so you can see this becomes pretty big pretty quickly. And how is this helpful? Well, what you can do is you can actually just remove all of these that don't change state. Right? And that leaves you with what, 4? 4 out of 16 or something like that. Now, if we have a look at current state of the machine, we could say it is currently on. And the X is 1, and the Y is 0. Okay, so this is the current state. We plug that in here. Well, maybe I should have done it in the correct order. X is, Y is 0, and we're currently on. So all we have to do is match this up. And then we know, hey, the next state. Right? But if this was like this, well, we can't find that state in this table. Therefore, the next state stays on. Alright, I hope that was a decent enough explanation what a finite state machine is, what it's used for, etc. And now let's move on to my implementation of it. I decided to implement mine using a 16-bit integer split into 2 parts. So kind of like what we were seeing up here, the state is one column and then the inputs are on the left. Very similar here. But this is binary. So let's just imagine that the state here is off, off, and then these are the inputs, so this is x1, right? Let's go back to the original diagram that we had. Here, off, on, okay, x equals 1, and x equals 1, very simple. Alright, now, we imagine that we currently have the state off, and then x is 1, and that's the first input, x, so the inputs start down here and go that way. Well, they don't have to, but that's the way I've programmed it. So you've got 12 inputs, and these are all Boolean values. If you think about Booleans, the general implementation of a finite state machine will probably use integers or Booleans or something to say, okay, what's the state, or an enum, right? So enums are generally represented by integers. So let's say you've got state on and off, right? What that's going to actually look like in binary, well, maybe I should, because it'll be easier to understand. Okay, so we've got 4 zeros. Let's say these are probably going to be 32-bit integers, which means there's going to be 28 zeros what's that? That's 16. Okay, and now finally we're getting to the part where we can actually tell, is this on or off? And it's off. And so we did all those zeros, and then finally we read the last one and oh, it's a 0. Okay, so on is like same thing. I'm not going to write them all right now, but instead at the end here we have a 1, right? So we've actually got this huge amount of space here that's just not being used. And you know, you could say, well, modern computers, who cares? We have enough RAM, we have enough whatever, doesn't really matter, does it? The answer is probably not, but maybe. If you're going to port your game to a platform like the Nintendo Switch, this kind of stuff might matter. If you care about having a lot of things happening, and let's say all of them, let's say you've got like 100,000 entities on the screen and they all have a finite state machine, well, you're going to want those finite state machines to be as small as possible, because otherwise you're going to be running from CPU cache off to the RAM all the time, and that's really slow. Right, so you want to minimize the amount of space that you're using for stuff like this. especially because it seems so innocuous, like, oh, just a boolean here or there. But if everything has this, then you're wasting, what is that, 28 bits per state machine per entity. So yeah, it can add up. Is it going to in this game? Maybe not, but it was pretty fun to program, so that's worth it in my book. And I got to learn a bunch of stuff, and hopefully you get to learn some stuff if you watch this video. Alright, so I've decided to use 16-bit integers because I thought that was a good size. So we have 12 states, sorry, not 12 inputs, so X, Y, A, B, C, whatever, and they can be either on or off. So we treat these bits as individual Boolean values, basically. And then the states is just a 4-bit int, which is 0 to 15. So if you need more than 15 states, then this is not going to work very well. I'm hoping that I don't run into that limitation, but if I do, it's going to be no problem. Or something down here? Oh, I thought it did. It's going to be no problem to just expand this out to a 32-bit integer, and then use the maybe like, you know, 8 bits or 12 bits for the state, and then the rest for inputs or something like that. That's not a big deal. I can change it later. But for now, I'm trying to get as much as I can out of a small amount of space. Now the way this works is, well, this is basically the table that I showed you before here, except for this simple machine, right? And it's only got the 2 transitions that actually change the state. So here we can see, you know, the X input is 1, the state is 0. So then we actually go and we have this lookup table here, which is just at the next memory block. And I've actually stored the results in 4-bit increments. So result 0 is here, so current state is 0. We want to switch to the next state, which is 1. If the current state is 1 and the X is 1, then we want to switch to the next state, and we go over here, which is 0. Pretty simple stuff. If you want to get an idea of how much space this is saving, imagine that you have, well, it could be saving space or it could be saving computational power, right? Imagine you have a finite state machine, and then when you're continually running a function called, like, you know, check. Oh, my pen went weird. Continually running a function like check on state, right? And then you say if input X equals 1, and then call my finite state machine and change the state, change to 1, whatever, or off, however you define this, right? You're actually running this function every single time, which takes not much processing power, but you can imagine if the state, you know, let's say you've actually got the 12 inputs here, and then you want to calculate them each time and do all this stuff. I think it'll be way more expensive than just having this little table here in memory, which takes up not much space at all. So for instance, this is 2 bytes, 2 bytes, and then this is 2 bytes, because you can't, well, you can, but this space here is just going to be unused by the program until I add a third transition state here, and then this one will be right. So the maximum amount of space that can be wasted with this is 12 bytes, which I think is pretty good. Whereas if I went with the approach like this, then every single state I am wasting 28 bytes. And maybe, you know, you could say, well, why don't you just use an 8-bit integer? Okay, sure. But then every single state I'm wasting 4 with an 8-bit. Say we use 8 bits. right? And then unless we have more than 16 states, which maybe we do, okay, fine. That's definitely acceptable. But in most circumstances, we're probably not going to be using more than 16 states. So we're going to be wasting all of these for every single state. And then we're also going to have to increase the size of this table to be whatever, let's say a 32-bit, to accommodate the new size of the states and plus the inputs. So that could be wasting, let's say we only use the extra 4, and then what's this, 16 and then 20, so we're wasting like 12, another 12 per transition state as well. That adds up pretty quickly. I think that's all I had to talk about. So actually, you know what, yeah, that's all I had to talk about. That's all I have to talk about, so thanks for watching, and I hope you learned something. Catch you.